Hello, algebra students. Mr. Lawrence here, and this is your flipped lesson. We are going to be talking about adding and subtracting rational numbers. Now, rational is a very important word that you may not totally understand. See, there's two types of numbers, and I'm going to switch to another page here. Hold on one second. We have rational numbers, who have a symbol, by the way, and their symbol is a Q. And then we have irrational numbers. Oops. Started to make the symbol for irrational. Irrational, and their symbol is an I with an extra bar. Okay, and if you ask yourself what does ir mean, the prefix, it's means not. Okay, so the translation of irrational would be simply not rational. All right, now how can you tell if a number is rational? Well, first of all, rational numbers include all fractions. All fractions. For example, they include 1/8. They include -2/15. But they also include 5. Why? Because I can write 5 as a fraction, can't I? Isn't 5 over 1 the same as 5? Well, of course, 10 over 2 is the same as 5, and 15 over 3. All those fractions are rational. Therefore, 5 is also rational. Um, Now, they also include decimals, and the decimals have to fit in one of two types of categories. Decimals that either A, end. For example, 5.0. That's a decimal that ends, right? Okay, 2 and 1400ths. That ends. 7 and, hold on one second, 1005, 10,000ths. Yeah, tens, hundreds, thousands, 10,000ths. Yeah. Uh, those decimals all end. Therefore, they're all rational. Or the decimals must repeat. A rational number is a number that can be expressed as a fraction, or it's expressed as a decimal that terminates, ends, or repeats. Okay, a repeating decimal, of course, would be like, 0, 6 repeating, which of course is the same as 2/3. Hey, look, I could turn that into that fraction, so of course it has to be rational. You might have like 1/7, which is the same as 0.142857. And all 6 digits repeat. That goes on 0.142857, 142857, 142857, 142857, forever and ever and ever. It repeats that pattern of numbers. Those are your rational numbers. Now, irrational numbers, they have a very famous member. That would be pi. And why are they so famous? Well, they do include decimals, but they include their decimals neither end nor repeat. Okay, so if I'm an irrational number, I go on forever and ever and ever, and there is no pattern to my repetition, or excuse me, to my continuing. It doesn't mean the same digit doesn't show up more than once. It means there's no pattern to it. Like in this 1/7 in blue over here. Yeah, this is the same as 1/7. It goes 142857, and then it gets 142857 again. This one here, which would be pi, 3.1415, it keeps going and going and going, and there is no repetitive pattern. Okay, now, by the way, many square roots are irrational, like the square root of 10. I'll bet you don't know a number times itself that equals 10. And if you were thinking 5, please pour some ice water on your head and then slam your thumb in a drawer, because 5 times 5 is not 10. Okay, there is no number that times itself that equals 10. That's an irrational number. A calculator can tell you this big long decimal, but it's only an approximation of it. The square root of 11 is irrational. Square root of 12, square root of 13, square root of 14, square root of 15. And of course, when you get to the square root of 16, it goes over here because the square root of 16 is plus or minus 4. So we're going to be talking about adding and subtracting rational numbers. We might have a problem with fractions, which we've already practiced. We might have a problem with decimals. They're all rational numbers. So let's quickly review this fraction subtraction problem. I like to say that, fraction subtraction. All right, so I need to turn these both into some denominator so I can just simply count how many I have. And it looks like my denominator is going to be 24ths. Notice I changed to an addition problem and changed the sign there. Don't have to do that, but I like to. Let me see here. I count by 8, so I'm going to get 8, 16, 24. Stop! Okay, that's because 8 goes into 24 and 3 goes into 24. So I'm going to multiply 8 by 3, and I'll multiply 3 by 3. And I'll have 9 24ths, okay, plus, and I'll multiply the denominator by 8 and the numerator by 8. Remember, I'm only multiplying by a very special form of 1. Negative 8 over 24. All right, well, I have 9 24ths, and I take away 8 of the 24ths. I'm left with 1 24th. Pretty simple stuff. Now, if I come over here, I have 5 and 7 tenths, negative 5 and 7 tenths, plus 2 and 3 tenths. Now, before we do that problem, I want to point something out to you. If I do 10 minus 5, I get 5, right? What's 5 minus 10? Well, you notice that the 10 was positive and the 5 was negative, and I got a positive 5, right? Well, in this case, the 5 is positive and the 10 is negative. So I'm going to get the same answer, only the inverse of it, because I'm using the inverse signs. The 5's change signs, the 10's change signs, and so my answer will be the same in change signs. So if I ask you what 6 minus 7 is, shouldn't be any big deal. You know that 7 minus 6 equals 1. Well, then 6 minus 7 must be negative 1. I'm repeating this over and over because it is so important. So when I have a problem like this, I know some of you get bent out of shape over it, and there's a pretty standard algorithm for doing it. You line up your decimal points, and that's a good way to do it. I might do a problem like that later. Hold on one second. Okay, sorry about that. I had to pause for a second. It looks like things are okay. When I look at this problem, I don't see 5 and 7 negative 5 and 7 tenths plus 2 and 3 tenths. I see this problem here. I see 57 minus 23, which is a very simple problem, 34. And I know it's positive, or it's going to be a negative because the 57 is negative and the 23 is positive, right? And since I'm dealing with 5 and 7 tenths and 2 and 3 tenths, it won't be 34, it'll be negative 3 and 4 tenths. Yeah, that's pretty simple, isn't it? Now, of course, you could do it more traditionally, and like I said, I will do one more traditionally. When I look at this one here, I think about money. I think about having $4 and a penny, because that's what $4 and a penny would look like, written down, and I lose 50 cents. Hopefully you weren't thinking this was a nickel, because this is the same as 50 cents. It's 5 tenths or a half. Half a dollar is 50 cents. A nickel would look like this. Not the same thing at all. All right, so if I have $4 and a penny and I lose 50 cents, well, if I had $4 even and I lost 50 cents, I'd be down to 3.50. But then I actually had another penny, so I'll be up a penny. So my answer is $3.50, 51 cents, or in this case, 3 and 51 hundredths. It's not actually money in this case, but I treated it like money because it would be easy to do. Now, when I have a problem like 4, it gets a little more awkward. It doesn't look like money to me. So I'm going to take the 6 and 81 hundredths and I'm going to add a 0 to that. Why am I doing that? Because I've got 2 digits past the decimal, and here I have 3 digits past the decimal. Now I'm going to subtract 0 and 3 1,000ths. Now, if you think about it, don't make this hard. If I had 810 and I took away 3, I would get 807. So I'm going to get, excuse me, I'm going to get 6 and 807 thousandths. Just like that. I can do it more traditionally if you like. I'll write it down traditional fashion. And let's see, I can't take 3 away from 0, so I have to borrow. Turning that into 10. 10 minus 3 is 7. 0 minus 0. 8 minus 0. 6 minus 0. Notice I get the same exact answer as here, but it was a lot easier to work with. Okay, that's your video for tonight. We'll get some practice with this kind of stuff tomorrow. Mr. Lawrence signing off. Have a good night, everybody.